Dichloromethane. Dichloromethane is a molecule made of these pieces: one carbon atom, two hydrogen atoms, and two chlorine atoms put together like this. A more streamlined way of depicting the molecule is with a skeletal structure. In skeletal structures, carbon atoms are replaced by kinks in the chain of a line, and the hydrogens on them are implied. Dichloromethane occurs in small concentrations in a few places in nature. One is in volcanic eruptions. The gases of volcanic eruptions contain some dichloromethane. It also is released in small quantities above some wetlands, dichloromethane. And it can also be released by some macroalgae in the ocean, and the dichloromethane then will be released into the ocean in that way. Humans use dichloromethane for a number of things. The biggest one is as a solvent. So for example, caffeine will dissolve in dichloromethane. And so if you want to remove caffeine from coffee beans to create decaffeinated coffee grounds, you can take the coffee beans and dunk them into dichloromethane. The caffeine in the beans will leach out into the dichloromethane. Most of the flavor molecules will stay in the beans. And then you just strain the beans out of the dichloromethane, and the caffeine is left behind, dissolved in the dichloromethane. So it can be used to create decaffeinated coffee grounds. It's one of the ways people make decaffeinated coffee. It's also used as a propellant in some spray cans. And it can be used to create foams with sort of plastics. So plastics that might naturally be hard, you can blow some dichloromethane to create very small bubbles in them. And the dichloromethane bubbles will pop, the dichloromethane can escape, and their holes will be left behind. And that can create something like this sponge here, whose holes were created by little dichloromethane bubbles that were sort of blown into the plastic material. Finally, dichloromethane can be used as a paint remover. If you apply dichloromethane to a paint, the paint will dissolve. The hardened dry paint will dissolve into the dichloromethane, and then you can take a rag and scrape the wet mixture off and remove the paint from an object. Safety with dichloromethane is important. You can summarize the safety issues associated with dichloromethane in these fire diamonds or safety squares. The blue box on the left represents the hazards to your health presented by dichloromethane. It's on a scale from 0 to 4, where 0 means you have no health hazard and 4 means you'll have a quick death on exposure to the molecule. Dichloromethane is a 2. It can cause skin irritation, and it can be absorbed through your skin, which can lead to chemical burns. So when you're working with dichloromethane, you want to make sure you're wearing gloves and that you're also wearing goggles that protect your eyes all around them. It also, if you breathe it in, can lead to dizziness, fatigue, nausea, headache, numbness. And if you breathe it in at higher concentrations or for longer periods of time, it can do damage to your optic nerve, it can lead to hepatitis. It's metabolized in your body to carbon monoxide, so it can lead to suffocation and even coma and death at very high or prolonged exposures. There's also some evidence, at least in animals, that it can be carcinogenic. There have been some studies that have shown that dichloromethane can lead to lung, liver, and pancreas cancer in lab animals. So there's a concern about that, although nothing definitive has been published about that for humans yet for dichloromethane. So that's what it means for dichloromethane to have a 2 in that health box. The second box, the box at the top, is the red one, is representing the flammability risk of dichloromethane. That's also on a scale from 0 to 4, where 0 means a molecule will not burn, you cannot light it on fire, and 4 means it's a flammable gas at room temperature. Dichloromethane is a 1, and so if you get it really, really hot, like above 100 degrees Celsius, which is the boiling point of water, it can form a flammable vapor, and it means it also can burn. So if it's exposed to fire or sparks, you could light dichloromethane on fire. So you want to make sure you keep it away from sparks and fires and excessive heat. The yellow box on the right tells you about the molecule's instability or reactivity. It's also on a scale from 0 to 4. Here, 0 means the molecule will not explode, and 4 means it could explode at room temperature if disturbed. Dichloromethane is a 0, so you can shake it up at room temperature. It's not going to explode. The white diamond at the bottom that's left blank means that there are no special considerations you have to think about when you're working with dichloromethane outside of the health, flammability, and reactivity considerations. Let's try to visualize dichloromethane. We've seen how you can represent it in a streamlined way through this skeletal structure, which is representing these atoms here. But this is a two-dimensional representation of a three-dimensional molecule. Here you can see that the carbon in the middle of dichloromethane is tetrahedral. You can also see that the chlorine atoms are really big. They're much bigger at the top left and top right than the two hydrogen atoms at the bottom of the molecule. Finally, this three-dimensional representation is also depicting the stickiness of this molecule. Stickiness has to do with the charge. Chlorine is an electronegative element, which means it pulls electrons to itself. So these two chlorine atoms pull electrons to themselves and become slightly negative. That's represented by the red color in this electrostatic potential map. That's the name for these colored three-dimensional depictions that tell you where the charges are. And because chlorine is pulling electrons to itself, it pulls electrons away from whatever it's bonded to. You could see here, that's this carbon. So the carbon is losing negative charge, which means it becomes slightly positive, and that's being represented by the blue color in this electrostatic potential map. Now, these bonds are not still and static. These bonds vibrate around 10 trillion times per second. So to give you a sense of how this molecule looks when it's moving around in real life, here's a simulation showing those single bonds vibrating and twisting and turning. I've played that simulation at around 1 vibration per second, which is a speed we can use to track and follow and sort of intuitively understand the vibrations and twistings of the bonds. But at room temperature, this molecule, those bonds, could vibrate around 10 trillion times per second. So let's speed this up to get maybe a sort of better sense of what the molecule might actually look like. Let's speed it up just 20 times. Now let's speed it up 400 times. To understand the motion of a molecule in reality, you would have to speed this up more than 25 billion more times before you got to the real amount of vibrations and twistings and turnings happening in a dichloromethane molecule at room temperature. 1 drop of dichloromethane has more than a quintillion molecules. That's more than the stars in a billion galaxies in 1 drop of dichloromethane. As you zoom out from the molecule to the scale that we live on, the macroscopic scale we live on, the individual molecules merge together like pixels in a screen, and what our brain perceives is a clear liquid, as you can see here at room temperature. Physical properties of dichloromethane. So once you zoom out and you have these quintillions of dichloromethane molecules existing together next to each other, they have certain personality traits as a community. They stick together and act in a similar way as a community. And those community traits are called the physical properties of dichloromethane. You can look physical properties up in reliable handbooks like the CRC handbook on the left here and the Merck index on the right. One physical property is the phase of the molecule, whether it's a solid, liquid, or gas. Whether it's a solid, liquid, or gas depends, among other things, on the temperature. In the laboratory, dichloromethane will be a solid below negative 142.1 degrees Fahrenheit. It'll be a liquid in between negative 142.1 and 103.3 degrees Fahrenheit. And if you heat it above 103.3 degrees Fahrenheit, it'll turn into a gas. Compare this with water. Water freezes at 32 degrees Fahrenheit. So dichloromethane stays a liquid to much colder temperatures than water would. On the other hand, water boils at 212 degrees Fahrenheit. So dichloromethane will evaporate much, much sooner than water would. It will start forming a vapor in the air much sooner than water would start to turn into steam. As a scientist, you want to not just think in terms of degrees Fahrenheit, you also, of course, want to think in terms of degrees Celsius. And so for comparison, dichloromethane would be a solid below negative 96.7 degrees Celsius, a liquid between negative 96.7 and 39.6 degrees Celsius, and a gas above 39.6 degrees Celsius. Again, compare with water. Water freezes at 0 degrees Celsius, so dichloromethane would stay liquid at much colder temperatures, and water boils at 100 degrees Celsius. So dichloromethane would turn into a gas at much lower temperatures than water would. You can use these freezing points and boiling points to separate molecules. For example, if dichloromethane is in a mixture, you can cool the mixture down so that dichloromethane will solidify out of it, and the other molecules would stay liquids, and then you can just strain the solid from the liquid. When you separate molecules based on the freezing point, it's called crystallization. On the other hand, if you have dichloromethane in a mixture and you want to separate it, you can also heat it up. You could heat it up so that the dichloromethane evaporates, but whatever else is in the mixture doesn't. And then you can collect those vapors on, for example, the underside of a piece of glassware, and then let that drain into another container. When you separate molecules based on their boiling points, it's called distillation. Another physical property, another sort of population community property of these dichloromethane molecules is their solubility. Solubility is significant because it creates structure in fluids. So let's think about the solubility of dichloromethane in water at room temperature. Solubility, whether things mix or not, really has to do with how spread out charges are on molecules. Water has oxygen in it, which is very electronegative, so it pulls electrons to itself and becomes slightly negative. And anything the oxygen is bonded to loses those electrons and becomes slightly positive. So every atom in water has a charge. So water is said to be very polar. It's very sticky. These charges will want to stick to opposite charges on other molecules. And if in a drop of water you'd have trillions of water molecules and they'd all be sticking to each other. If you introduce another molecule, like dichloromethane, and you're thinking about whether that dichloromethane will insert itself into the water, that depends on whether the water will want to stick to it or not. As you can see here, there are some negative and some positive charges on dichloromethane. So the positive, slightly positive hydrogens of water will want to stick to the slightly negative chlorines of dichloromethane. And the slightly negative oxygens of water will want to stick to the slightly positive carbons of dichloromethane. So they will mix a little bit. But as you can see, there's a larger stretch of green. That's where there isn't a charge. That's where the molecule is neutral in dichloromethane than there is in water. So dichloromethane won't mix perfectly with water. Water will still be more attracted to itself than it would be to dichloromethane, but it will mix a little bit. Dichloromethane will be slightly soluble in water. Specifically, 17.5 grams of dichloromethane will dissolve in each liter of water at room temperature. A final physical property to think about with dichloromethane, and it's especially important with dichloromethane, is density. Density is important because it creates structure based on sinking and floating. More dense objects sink, less dense objects float. This creates everything from the core, mantle, and crust of the Earth to the different layers of the atmosphere, and when air sinks and floats, differences in density create winds. The density of dichloromethane is 1.3266 grams per milliliter. Compare that with the density of water, which is just 1 gram per milliliter. So if you put dichloromethane with water, because dichloromethane has a larger density, it will sink and form a separate layer below water. Hopefully this video has given you a deeper sense, better understanding of the molecule dichloromethane.